So here we looked at what happens if, different variables are constant and we're changing different variables, right? So this was like a very sort of basic beginning to the whole related rate. So now let's go into, more of the types that we're going to see every day. Okay, let's come up with a few strategies to solve related rates problems, right? So first and foremost, you have to read through the problem and you have to highlight, you have to identify the variable for which the rate of change you are looking for and the variable or variables for which the rate of change you know, right? Then you have to develop a mathematical model. How does that work? Well, what are some things you could do? You can draw pictures, right? That's very important, very important. What is of utmost importance is you have a record of what quantities are constant and what quantities are changing, right? So distinguish what is constant from variables that change over time, because ultimately we're taking a derivative, right? And if we take a derivative of something that's constant, what is the derivative? 0. But if we're taking a derivative of something that is not constant, that is changing, then it's dx dt, dy dt, dh dt, right? Very, very different. Now, students are always very eager to put in values, right? Only constant quantities can be assigned numerical values at the start. Everything else, you have to take a derivative, then put in values. Again, because if you just put in values from the beginning, then everything will be 0. You get 0 equals 0, and you're like, oh, all reals. No. Okay? All right. Next, write an equation relating the variable, right, whose rate of change you're looking for with the variable that you know. Okay, a lot of times you will get a geometric formula like, tangent, sine, Pythagorean theorem, and so on. It could sometimes be like a physics equation, like rate over time and so on, or, Okay, once you have an equation, then you have to differentiate both sides implicitly with respect to t. All right? Okay. You're going to fall into the chain rule in here, right? Because you're going to be differentiating some other quantity, radius, height, whatever, area, with respect to time. And if you're differentiating with respect to a different variable, that's chain rule. Next, after you differentiate, substitute values for any quantities that depend on time. Okay, again, you can't substitute before you differentiate, all right? So only safe to do this after the differentiation step, okay? And then afterwards, you have to interpret your solution. Meaning, okay, now you have mathematically, whatever, r equals 5 and -3 and 0. But does that make sense in the context of the problem? Can your values be negative? Is there an implied domain in the problem, and so on and so forth? Okay? And then units. Okay? When we start looking at AP free response problems, and when we start looking at the rubrics set by the AP board to grade each of the problems, like each free response gets 9 points, you will see very, very often, you have like 3 points for this, 2 points for this, 1 point for this, 1 point, and then at the very end, 1 point for units. Okay? That's a lot of points. 1 out of 9 is a big percentage to lose because you didn't put your units. Okay? All right. So let's take a look at this problem. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising? This is a related rates problem. Two things are changing. You have the rate of one, you need to find the rate of the other. All right, so let's like color code, highlight, whatever, okay? Now, look at this. I have a rate here. The angle is increasing at a rate of 0.14 radians per minute. Okay, the angle is increasing. So the angle is changing with respect to time. That means it's d theta dt. And because it's increasing, the rate is positive 0.14 radians per minute. Okay. Now, how fast is the balloon rising? Right? That's what I need. What is that? How fast is ddt of something? ddt of what? Y, let's say, or h. Let's leave it in terms of y. So dy dt is equal to what? Now, what other piece of information do I have? I know that all this is happening at the moment when the elevation angle is pi over 4. Let me do that in red. Theta is equal to pi over 4. What else am I given? Okay, so I have some 500 feet here, right? A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. If this is the liftoff point here, this rangefinder is on the ground. It measures it on the ground, right? And it's 500 feet from here. So if this is the liftoff point, there is level ground, and then 500 feet away from it is the rangefinder. How do I know it's there? Because it also tells me that the rangefinder's elevation angle, this is an angle of elevation, and angles of elevation we know like start from, the ground up, right? So the angle of elevation is this right here. Okay, and this is y. So now that's what it looks like. Okay, so this is the balloon here. All right, now let's see if this is consistent with my problem. A hot air balloon is riding straight up, is rising straight up. And yes, if I go from here, it rises straight up. So that's my y, that's where my balloon is from the liftoff point. There is a rangefinder and it's measuring the angle of elevation 500 feet away, right? And so this is, what I need. Now, what I need to find is dy dt. Okay? So, what do I have? I have information on theta. What do I need? Y, right? Now, I need to come up with an equation that relates y to what I have, theta. So I can't do Pythagorean theorem here because that leaves out theta. That means what do I have to do? I have to do a trig one. So what do you think? Sine, cosine, tangent? Tangent, because I have y and I have the other leg x, right? So tangent of theta is equal to y over 500. Okay. Of in this whole thing, what's the constant? What is a constant? The pi over 4 is constant. What else is constant? I mean, the pi over 4 technically, like, that's the snapshot. The angle is changing, but we're looking at it when it's pi over 4. But what is never changing? The 500. All right? So that's your constant. Okay, now let's take a derivative of this. So I have secant squared theta d theta dt is equal to 1 over 500 times the derivative of y dy dt. I want to say this until the point where you wrote down tangent of theta is y over 500. That's like the most challenging part of this problem. And the rest is more methodical. But that, right, because no two problems are alike, right? So that's the part that's different. Okay, so now secant square theta. Now that I've taken a derivative, it's safe to put in values, right? But now, if I'm solving for dy dt, I'm going to move the 500 over to the other side. So 500 secant square theta d theta dt is dy dt. All right, now let's put in some of our values. So 500 secant of pi over 4 squared times d theta dt is 0.14 is equal to dy dt. Now, you may or may not have a calculator for this section, right? What's secant of pi over 4? Cosine of pi over 4 is 1 over root 2. So this is just root 2. Squared is 2 times 0.14. Right. It's 1 over root 2, which is root 2 over 2. And then the reciprocal will be root 2, no matter whether it's rational. Right, so it's 1 over root 2, which is root 2 over 2. Right, once you rationalize, right? Okay. Now, so this is 1,000 times 0.14, which is that dy dt is 140 feet per minute. Okay? Right, because it's like 1 over 500 times y. So if it was 3y, you would have done 3 times dy dt. Or 1 over 500 times dy dt. Okay? So the balloon is moving upwards at a rate of 140 feet per minute, which is reasonable, right? Okay. All right, take a look at this one. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car. Well, that's close to home these days. That has turned the corner and is now moving straight east, right? When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at a rate of 20 miles an hour. That's a rate. The cruiser is moving at 60 miles an hour at the instant of measurement. What is the speed of the car? I have no idea. I need a diagram. Okay, so let's do a diagram. A police cruiser is approaching a right-angled intersection from the north. If he's coming from the north, then he's going southbound, right? So he is, okay, so this is where the police car is. He's going from here down. And then he comes to a right-angled intersection. The guy turns east, and he also follows him east. So that's that way. Yeah? Okay. Now, then it talks about the distance between them. So if this is the police, this is the car. Okay, this is the bad guy. Maybe he's a good guy. We don't know. Okay. Yeah, you can't make assumptions. So that's the distance between them, right? Now let's give these people some variables. We're going to call this y, because why not? We're going to call this x. That wasn't even meant to be funny. You can call them like, you can call the vertical X and the horizontal Y if that's your thing, but I mean, seriously, that's just silly. Okay, now, the distance between them and the car is increasing at 20 miles an hour. So if that's XY, we can call this Z. And what's increasing at 20 miles an hour? The distance between the car and the police. So Z is increasing at 20 miles an hour. So dz dt is 20 miles per hour. Okay, now the cruiser is moving at 60 miles an hour. What quantity is that? D what dt? The cruiser, that's the police, is moving at 60 miles an hour. Dy dt, now, is dy dt 60 miles an hour? It's not. Why isn't it positive 60 miles an hour? Because it's going in the negative direction, it's negative 60 miles an hour because y is decreasing. Y is going down at a rate of, or y is going in the negative direction at a rate of 60 miles an hour. Yeah.
The only thing I'm not understanding though is that if he's following the car, the police guy, I just understand why the distance is measured from here to there. Because wouldn't he if he's going there, wouldn't he I don't know, I feel like they meet and then he would turn there. If he's gonna see the car going straight east, he would have to be
So we're looking at like an aerial view. Like if now there's like a helicopter looking at them, right? So he's here and he's moving down on one street and the other guy is moving down on the other street. The general distance between them, might be increasing because let's say the car, right, that is being chased is moving like much faster, so now their distances is increasing. Okay, so what is it that we need? What is the speed of the car? That's what I need, right? The speed of the car. How do I write that? What is that? dx dt. That is the rate at which x is changing. What is dx dt? Now, okay, so we have a little bit more information here. All this is happening when the cruiser is 0.6 miles north and the car is 0.8 miles to the east, right? So we have that y is 0.6 miles and x is 0.8 miles. We also have that. Okay, now we can use that to find z. But why do we even need z? What is the equation that's going to relate x, y, and z here? Pythagorean theorem. X squared plus y squared is equal to z squared. Are any of these constant? No, y and x are changing, and so is z. So none of these are constant. So if there is no constant, don't put any numbers in just yet. Let's take a derivative. 2x dx dt plus 2y dy dt is equal to 2z dz dt. Okay, all the 2's go away. Now, I need an x, I need a y, I need a z. I have an x and a y, I need my z. So coming back to the information, right? Y is 0.6, x is 0.8. So x 0.8 squared plus y 0.6 squared is equal to z squared. And if it's 6, 8, then the other side of the triangle it's 3, 4, 5 triangle or a 6, 8, 10 triangle. So these Pythagorean triples, if you have a right triangle, which is, 3, 4, 5, any multiple of that is also going to work. So it could also be 6, 8, 10. right? Any multiple of this will also work. 6, 8, 10, 9, 12, 15, and so on, okay? So here I have 6, 8, this will be 10. So Z is equal to 1. All right, let's plug these in. X 0.8 dx dt plus y 0.6 dy dt is negative 60 equals 1 dz dt is 20. So finally, blah, 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 solving, adding, subtracting, multiplying, dx dt is 70 miles per hour. Okay, wow, I got a positive value. Does that make sense? I see some people nodding yes. Yeah, that makes sense because x is increasing. X is moving to the left. No, it's not. It's moving to the right. So that's the positive direction. Okay? All right. These are all, what's the word? Like stereotypical related rates questions. Okay? If you think of related rates, or if I think of related rates, I think of an angle changing, like tangent. I think of, x, y, z, Pythagorean theorem. And then another thing that comes to my mind is a conical tank. What the heck is a conical tank? Well, that's example 6. Water runs into a conical tank at a rate of 9 cubic feet per minute. What is a conical tank? It's a, huh? No, not really. Do you know what a conical tank is?
I imagine
it's a, yeah, but the term conical tank, it's a tank in the shape of a cone, right? Right. So the tanks, there should not be an S there. The tank stands point down and has a height of 10 feet and a base of radius 5 feet. So this is how, this is how the tank looks. Okay, that's the tank. It's got a height of 10 feet and a base radius of 5 feet. Okay, so that's a cone made of, like, I don't know, metal, plastic, PVC, whatever, right? It's got a height of 10 feet, radius of 5 feet. Of these two quantities, which is constant and which can change? Okay, she says the 5 is constant. He says the height is constant. What do you think? Okay, so either neither of them are right, or both of them, or one of them. Okay, so this is the actual construct, like the metal, the tin can. This is not changing. Okay, it's an actual constructed can. None of these are, this is like the vessel itself. Okay, both of these are constants. They're not changing. So then what is rising? Water is now running into this tank at a rate of 9 cubic feet per minute. So water is filling into this tank. Okay, at a rate of 9 cubic feet per minute. Now that sounds like a change in volume to me, right? So dV dt of the water is positive 9 cubic feet per minute. How fast is the water level rising, right? So what I need here, so this, just that, is H. Okay? I need how fast is the level of the water rising. So what is dH dt? When is all this happening? When the water is 6 feet deep. Okay, the point at which the water is 6 feet deep. Okay, so here's how we do this. You're always going to do this in the same way. So look at what I have here. This much, right, from the top to the bottom, we said is 10. Is that right? Okay, now, this is happening when H is 6. Okay, so look at what we have here. If you take a look, whoa, I didn't mean to erase that. If you take a look, we have proportional triangles. I have 10 and 5, right? And then inside of that, I have just the amount of water, which is H and some value R. Okay? And now, how do we do proportional triangles here? R over H is equal to 5 over 10. Okay, proportional triangles. So when H is 6, R is 3. Okay. So we have volume and we have H. So we have to write an expression that relates volume to height, right? So volume is 1 over 3 pi r squared H, right? Okay, now. Okay, so here I have two variables, right? Let's see if you can eliminate one of the variables. I want dH dt, so I want H to stay there. But can I eliminate the radius, the R variable? From here, what is R if you solve this? It's H over 2. Okay? So that's 1/2 here. So R is H over 2. Is that right? So here, V is 1 over 3 pi H over 2 squared times H. So V is, here we're going to have a 4 times 3, so pi over 12, H cubed. Okay, so now let's take a derivative. dV dt is equal to, the 3 will come down, times pi over 12, H squared, dH dt. So dV dt is pi over 4, H squared. Do we have the value for H? Here, highlighted, 6 feet deep, right? 6 squared. And what's dH dt? That's what we need to find. All right. So what was dV dt? 9, right? So 9 is 36 over 4, 9 pi dH dt. So finally, dH dt is 1 over pi. Okay, plugging that in the calculator, dH dt is approximately 0.318 feet per minute. If you don't have your calculator, then it's 1 over pi feet per minute. Does it make sense that H is positive? Yes, because if the volume is increasing, so is the height. Because, like, if I solve this, divide by 9 pi, divide by 9 pi, then it'll be 1 over pi. Right here. Okay? So I had 9 equals 9 over 9 pi dH dt. I divide by 9 pi. Okay. Another very, very, like, famous typical problem is somebody walking with a shadow, right? And that's number 7. A woman 5.5 feet tall walks at a rate of 6 feet per second towards a street light that is 22 feet above the ground. At what rate is the length of her shadow changing when she is 15 feet from the base of the light? Okay, so here's the woman. She's walking towards a street lamp. So here's the street lamp, right? It's 22 feet above the ground. And we're assuming that when the, people put it in, they put it in straight, so it's a 90-degree angle there. Okay, now, when the person is here, she's 5.5 feet tall, right? So let's say she's here, right? That's her. The shadow, the lamp is going to cast a shadow on her, right? So where is her shadow going to be? This is going to be her shadow, this part of it, right? And the woman is 5.5 feet tall. Okay. So a woman 5.5 feet tall walks at a rate of 6 feet per second toward a street light that is 52 feet above the ground. So we know that that's the length of the shadow, and we're going to call this X. The woman is walking towards the street lamp. So when she's walking at a rate of 6 feet per second, she's covering that distance X. So dx dt is 6 feet per second. Huh? 6 feet per second? That's pretty fast. All right. She's also very tall. No, she's not. She's 5 feet tall. All right. At what rate is the length of her shadow changing when she is 15 feet from the base of the light? Okay, so now here. So look at this X value, right? Is X, so X is the distance between her and the light post. Is X increasing or decreasing? It's decreasing. Even though so it's decreasing, so this is negative 6 feet per second. Because I drew the triangle this way, it doesn't tell me that she's moving to the west or to the east. There is no direction associated here. I could very well have drawn it, this way, so that now she's moving here, right, to the east or to the west. So this is not a directional thing here. This is the fact that her distance is decreasing. The distance between her and the light post is decreasing, right? So it's negative 6 feet per second. Okay, so what do I have now? I have another proportional triangle, right? Another set of proportional triangles. So I have a small triangle to the left and a larger triangle to the right, right? Like the whole thing is a larger triangle. So 5.5 over S is equal to 22 over the entire side of that large triangle, which is S plus X. And what I need is the rate at which her shadow is changing. So what I need is ds dt. All right, let's cross multiply. 5.5s plus 5.5x is equal to 22s. Okay, and now what? I take a derivative, so it's 5.5. Is there anything we can combine here? Yeah, minus 5.5, right? So 5.5x is equal to 16.5s before I even take a derivative, right? Because I could combine like terms here. So now 5.5 dx dt is 16.5 ds dt. It's 22s. Yeah. I hate it when the same problem has, I shouldn't have called it s. I hate it when I have like s and 5 in the same problem. All right, so 5.5, what's dx dt? Negative 6 equals 16.5 ds dt. So ds dt is negative 2 feet per second. And now you have seconds is s. Okay. Yeah. So water is being poured at a rate of 25 cubic centimeters per second into a cylindrical glass this time with a base radius of 20 centimeters and a height 100 centimeter. So the one thing you learn in calculus, if nothing else, is how to draw perfect cones and cylinders, right? Because of these problems. So here I have a cylinder. It's a cylindrical glass or whatever, right? And there we go. The glass has a base radius of 20 and a height of 100. At what rate is the depth of water changing when the glass is half full? This is a question mark. But do you see how calculus people are like optimistic? Yeah, glass is half full, right? There you have it. Okay. Water is being poured in at a rate of 25 cubic centimeters per second. So that's dV dt is 25 cubic centimeters per second. Okay? At what rate is the depth of the water changing when the glass is half full? So what does that tell you when the glass is half full? That's when the height is 50 or the volume is yeah, it's half, exactly. Okay. All right. So if this is dV dt, and what is it that I need? dH dt. So now I need an equation that will relate V to H. And so that's V is equal to pi r squared H. Okay, now I have some things that are constant here, right? Pi is the radius constant here. The radius is known, it's a constant. It's 20 squared H. V is, so V is 400 pi H. dV dt is 400 pi dH dt. Okay, what's dV dt? 25. So 25 over 400 pi dH dt. So dH dt is 1 over 8 pi, which is 0.0199 centimeters per second is dH dt. Okay.